Let's get started. So we continue our study of classical tensor analysis. So yesterday we introduced the summation notation and the Kronecker delta symbols. In particular, not just the two indices, not just the Kronecker delta with two indices, but also the so-called Levi-Civita symbol. And we also use that to study determinants. Okay. So in the last section, namely the determinant, we left one example. Okay, we didn't have time to cover that last example, so we will do that today. Okay, so let's do that. Here, this example. Hi Vernon. Thank you so much for joining the stream. This is the last example of the section determinant. By the way, we're still following the same book, Vector Tensor Analysis by Harry Lass. Classic text, and it's great. Each individual chapter is perhaps worth its own coverage. So, in my opinion, this is the classic version, at least, equivalent of Baby Rudin when it comes to vector calculus. It's that good. Hi Ming, hi DMC. So here we're doing example 10. Let yi be a function of n variables. Yi be functions of x1, x2, all the way to xn. And assume that the Jacobian determinant dy dx is non-zero. We will show the following identity, tensor, or no, just the identity in the summation form. So this is the formula for the second order derivative of the inverse function. So the second order derivative of the inverse function, namely the Hessian matrix, looks like this. So d squared x mu, d squared x mu over dy k dyj, the second derivative. Okay, and the result is as follows: is minus dx alpha over dyj and dx beta over dyk, and dx mu over dyi, and then times the second derivative, which is d square yi over dx beta dx alpha. So it's a pretty complicated formula. Okay. So before we prove it, let's first observe the structure and see if there's anything interesting we can say. Hi, Marco. So on the left-hand side, of course, that's the Hessian matrix of x as a function of y. On the right, the first factor looks like just the Jacobian, right? Just the Jacobian of x relative to y. And then you get the Jacobian again, although different elements this time, different elements completely. And then you get also the Jacobian element, and finally you get the Hessian element of y with respect to x. So this is highly complicated. So imagine if you try to write this without the summation notation. So how many summations are there? Let's just take a quick count. So the free indices are mu, k, and j. On the right, we got alpha repeated, so alpha is summed over. Beta is repeated, beta is summed over. J is repeated, so actually j is not. J is on the left. The j is the free index, and I needs to sum over. So that's a triple sum. So there are three sums on the right hand side. Okay. So how do we show this? So let's begin with a simple identity proof. So it takes a little bit of a trickery to do this sort of proof. Perhaps it is not so surprising that we would start from the Kronecker delta relation. So imagine this. So think about the situation in a vector matrix notation. So here, y is a function from Rn to Rn, or subsets of Rn to subsets of Rn, right? And the inverse function would be a function from a subset of Rn to Rn as well. Oh, hi, Matthew. So if you want the determinant, so if you want the derivative of the inverse function, you probably start from something like this. So I equals j times j inverse, and then differentiate both sides. Right? That's literally what we're doing. But we're going to do this using the index notation. So on the left-hand side, the indices are just the Kronecker delta symbol, delta ij. Remember yesterday, since yesterday we're starting to write the Kronecker delta symbol as delta upper I lower j. I'm pretty sure there's going to be delta ij like this, okay, two lower symbols later on, but they take on different meanings. Okay, so far we have been just working with this one. Okay, so far we haven't talked about the meaning of upper and lower indices yet. Hi Arthur, thank you very much. Hi guys, thanks for joining the stream. So anyway, here we have this relation between the Jacobian matrix and its inverse. So in notation, in indices form, it reads delta ij equals dyi over dx alpha, and then dx alpha over dyj. That's it, right? So here, this is a identity matrix element, and this is the Jacobian of y with respect to x, and this is the Jacobian of x with respect to y. Starting from that, and we're going to differentiate. And what do we differentiate with respect to? Obviously, you should differentiate with respect to y, right? Because we're interested in the derivative with respect to y. So we take the derivative with respect to yk, partial derivative with respect to yk, d over dyk on both sides. Left-hand side just gets 0, because there's just a bunch of constant. Right? Doesn't matter it's 1 or 0, they're constant. So differentiating that gives you 0. All right. Just like when you differentiate identity matrix, always gets the 0 matrix. Right. So here now, if we differentiate the right-hand side, just use the product rule, and you get so dyi. So let's first keep this factor unchanged, dyi over dx alpha. Differentiate the second, so that's the second derivative, d square x alpha over dyk dyi. All right, so that's the first factor. Sorry, that's the first term in the product rule, and let's continue. And you would get now you have to differentiate the factor dyi over dx alpha. Okay, to do that, you need a second derivative, don't you? You need a second derivative, don't you? So you do a d. Hold on a second. Let's just write it slowly. Okay, d over dyk of the first factor, dyi over dx alpha, and then times dx alpha over dyj. Okay, dx over dij. So how do you expand that? Well, we can consider the chain rule. We can consider the chain rule because here you have a derivative of y with respect to x. So let's use a chain rule and write that as d over dx dx alpha. Yeah, actually that's not a good idea, isn't it? It should be x beta, because alpha is already used. So d over dx beta dyi over dx alpha, and then times dx beta over dyk, right? That's just a chain rule. You treat it as a single quantity, right? And then you apply the chain rule here. So what does that give us? Well, of course, therefore, this way you just get the 0 here is unchanged, and plus this is d square yi over dx beta dx alpha times dx beta over dyk times dx alpha dyj. Okay. Yeah, so far so good. So far so good. So yeah, so here use the product rule and the chain rule. So let's take a look at this expression and compare it with what we wanted. Right? We want something like this. Right? We want the second derivative of x with respect to y. So we want that. So how do we isolate that? Right? So that's the question. Because we can't just move this to one side and divide by this factor. You can't do that because there's summations involved. Right? There's summation. Actually, here there's a little bit of a confusion. This is yj. Okay. In the first term, there's summation involved. Alpha is summed over. You can't just move this term to the left and then divide by the factor. It doesn't work like that. So somehow we have to do some trickery here. So how do you say get rid of this factor? That's the idea. Well, we're going to use the Kronecker delta symbol again. So let's multiply both sides, because remember, Kronecker delta collapses indices, right? So that's the trick to it. So multiply both sides by dx mu over dyi. Dx mu over dyi. Let's see what that does. So on the left, you still get 0, and you get d x mu, okay, dx mu over dyi times this term. Okay, I was just going to copy paste. Not only it saves me time, but also it's more visually intuitive what we're doing. Okay, so just multiply that, and you multiply the same term to, sorry, the same factor to the second term. Right, that's the second term. It looks like a monstrosity. Okay. All right. So you get that. What's this thing? Huh? We multiply that for a reason, because this gives us the Kronecker delta. This is the Kronecker delta, delta mu alpha. This is the delta mu alpha, and then you can use that to change indices, right? Vermont yesterday spent like over 15 minutes trying to teach me that. Okay, I finally got it. So thank you very much, Vernon, again. So you see here, because you got a delta mu alpha, and it is multiplied by another term with another index alpha, same index alpha. So in that term, you just swap alpha to mu. That will be it. So here, therefore, 0 just becomes d squared x mu over dyk dyj, and then plus this thing here unchanged, I believe. Yeah, there's nothing can be done here, no? Because you see, here all the Jacobians, the first order derivative, I mean, or the first order derivative, I mean, all have x on top and y at the bottom, so nothing can be done here. No simplification available. But this is, I think this is what we wanted. Right, so this is very much what we wanted. So yeah, then we're done. See, you got 3 first order derivative of x relative to y, and you got this y relative to the Hessian of y with respect to x here, which is exactly what we wanted. So we're done. Okay. Okay. So that wraps up the chapter. So not the chapter, but the section on determinant. Okay. So because right now I wish to go through the main text of Harris. Sorry, not Harris. Harry Last. But quickly as possible. So I'm skipping problems which might bite me later. Okay, which might bite me later. So because starting from this section, I can already see there are some non-trivial exercises. So because I wish to go through the text as quickly as possible, I might need to come back, or at least we will come, or at least I will come back later, okay, to take a look at the exercise. Maybe not solve all of them, but perhaps identify useful identities sometimes hidden in exercises. Okay, all right. So now we're going to the next section. Okay, and today hopefully we'll get to the definition of tensors in its classic form. Okay. Anyway, so here we have this is section called arithmetic or vector n space. Pretty weird title, called arithmetic, comma, or vector, comma, n space. All right. Oh my God. Here we go. Okay. Here it says, now in the vector analysis studied in the previous chapters. By the way, this is chapter 8. Previous chapters are our classical vector calculus, div, grad, curl, and all those stuff. In the vector analysis study in the previous chapters, we set up a coordinate system with 3 independent variables x, y, z. We chose 3 mutually perpendicular vectors I, j, k, and all other vectors could be written as a linear combination of these 3 vectors. Of course, that's what we know very well. And then it continues, says, any vector could have been represented by a number triple, x, y, z. Right? So let's just draw a picture to describe what's going on. So previously, this is all well known. Okay, so you have x, y, z axes, and you got these coordinate vectors or unit vectors, I, j, k. Classic notation, I, j, k. In linear algebra, we usually write E1, E2, E3 instead to avoid confusion with the imaginary unit I. Right? So any vector can be represented by 3 numbers, like so. So imagine here you have a vector. Right? This vector can be written as 3 numbers, x, y, z, which is really a basis expansion. So it's xi plus yj plus zk. Right? And the unit vectors I, of course, these are so-called standard basis vector, right? 1, 0, 1, 0, 0 for I, and j equals 0, 1, 0, and k equals 0, 0, 1. Okay? So there you go. A system of mathematics could have been derived solely by defining relationships and operations for these triples. And we need never have introduced a geometric picture of a vector. Right, so that's the comment here. So we can just work with these triples from now on and forget about the image. Although that's not recommended, but still, you can do that. You can do that. So, for example, the 2 triples are defined to be equal if their components are defined to be equal. So let's write that down. Now you just simply work with triples. So A, B, C, and alpha, beta, gamma are considered equal. Definition are considered equal if their corresponding components are the same. Right, so this is well known. A equals alpha, B equals beta, and C equals gamma. All right, and we can define the so-called scalar product or dot product. Same thing. The book uses the term scalar product, which is also quite common. Scalar product. Alpha, beta, sorry, A, B, C. We're not gonna even write the dot, okay? Just write A, B, C concatenated with alpha, beta, gamma to mean the scalar product or the dot product, which is A alpha plus B beta plus C gamma. Okay, another well-known operation. Okay. And then it says vector product, differentiation, etc. can easily be defined. Addition of triples are defined as follows. So addition, once again, no news here. ABC plus alpha beta gamma is just component-wise addition. Right? We use that we reviewed all of those stuff quite extensively in our live streams on 3D rotations. In particular, part 1, the review on 3D vector algebra. Okay, and you got the scalar multiplication rule as well. Scalar multiplication rule, A times ABC, big A times ABC, where A is a scalar, is just big A times little a, big A times B, big A C. Right, so, okay, so far everything is familiar. Right, so these rules together defines the geometry of the 3D Euclidean space. So this is what the author called so-called arithmetic space of 3 dimensions. Perhaps this terminology is a bit archaic, okay, but at least in the context of the text, we know what this means. The so-called arithmetic space of 3 dimensions. Kind of weird by today's standard. That's okay. That's okay. It's still totally readable. Not a big deal. Oh, hi, Rico. Thank you very much. All right. So, and now we can, it says, it is easy to generalize all of this to attain the arithmetic end space. Taking a chance here just to clarify me. Basically, the difference between dot product and inner product is that the last is reserved for more general vector spaces. Yes, inner product is more abstract construction. So inner product is defined over abstract vector spaces. Okay, and it is defined axiomatically. So an inner product, for example, if you know what, let's just go there. My famous linear algebra module. Go. University of Waterloo, linear algebra 2. Yeah. This is typically how modern users use the term inner product. So for example, inner product, here you go. You start with an abstract vector space. So here let V be a vector space. Okay, and here it actually means a real vector space. It means the scalar multiplications uses real numbers as scalars. Okay, so the V is a real vector space. And inner product, V is a function that takes two vectors in V and returns a real that has these properties. So this is defined axiomatically. So from these definitions, you don't know how exactly you would calculate the inner product. You just know how it behaves. And of course, these properties are all inspired by the dot product in R3, R2, R3, Rn. Okay, so this is an abstract version of the scalar product or the dot product. And of course, the dot product is a special instance of the inner product. Okay, and this in particular is powerful. This definition here, the axiomatic definition, is powerful when you're dealing with infinite dimensional vector spaces like Hilbert space. Okay, so there's that. Okay, people commented, hi Andy. Christian, thank you very much for joining the stream. As my linear algebra book says, your friend will be mildly impressed when you tell them you're studying inner product spaces. Right. The dot product is one of the instantiation of inner product. Yes, pretty much. Yeah. Okay. So there you go. This is how modern users, modern writers use the term inner product. Okay. Yeah, there's some little bit of a time delay when it comes to chat and my own voice. I already knew that based on watching my own stream. All right. Thank you everyone for participating in the discussion. So here, all of this that we wrote before easily generalizes to n tuples. Okay, so and now you have the so-called, once again, probably antiquated terminology. Okay, it's called arithmetic n space. Arithmetic n space. Okay, probably just Rn. I think this is just Rn. But since we're reading the book, we're going to respect the terms that the author uses because it's okay. I think I mentioned somewhere yesterday that we as applied mathematicians are ambassadors of scientific communications. Okay, and it's important to speak the language of other fields. Okay, so now the delay is about 15 seconds, depending on your setting in OBS and YouTube. Oh, I don't want any delays. Okay, I'll check that out later. Okay, so here, arithmetic n space is just Rn. So elements of this space are just n tuples, familiar from linear algebra, x1, x2, all the way to xn. And these are all real. Okay, these are all real numbers. In particular, you got the basis vectors, basic vectors. It's called, I'll use the term that in the text, it says unit or basic vector. Okay. For all intent and purposes, these are just standard bases. You can set to ultra low to this, of course, means higher chance of internet interruption. Okay, pray to Lord that the internet is going to be okay today. All right, so this is the standard basis vector, and our notation is going to be Vn. Notation throughout the rest of the text is going to be Vn. Okay, anyway, and then it says, by a space of n dimensions, we mean any set of objects which can be put in one-to-one reciprocal correspondence with the arithmetic n space. Okay, so this is where things isn't considered completely rigorous by modern standard. Yeah, basic vectors should be standard vectors in basis, exactly. Yeah. I'm using the exact term used in the text, so we know what this means. So here, and then here it says, let me just put that down here. I think the author is trying to introduce the notion of a n-dimensional manifold, but it stops short of using the term for whatever reason. Perhaps the book came out in 1950, by the way. I'm not sure if the notion of manifold was considered standard at the time. Okay, but here's what it says. By a space of n dimensions, we mean any set of objects which can be put in one-to-one reciprocal correspondence with the arithmetic n space. We call the correspondence a coordinate system. The one-to-one correspondence between the elements of points of the n space and the arithmetic n space can be chosen in many ways. And in general, the choice depends on the nature of the physical problem. Is x restricted to real? Yes. Here, I wrote Rn. They're all reals. Okay? We don't deal with complex numbers throughout the series. Okay? So let's just draw a picture to see what's going on. So for example, let's draw, for example, this torus-shaped thing to indicate a general quote-unquote space. But really, it should be a manifold. It really should be a manifold, yeah. So what they're saying is, if you look at a small patch of that set, and you can build a bijection between a subset of Rn, okay, the arithmetic M space, so-called. So let's say, for example, here, let's just use this as a visualization for Rn. All right, and this green little patch on the manifold, let's just call it M, corresponds to a green patch, corresponds to another patch, say also a green patch in Rn. So, and in particular, I think in modern terms, we want both sets to be open. Why do we want sets to be the sets to be open? Well, open sets gives us the most general notion of nearness, and basically when you do calculus, okay, when you do calculus, in particular differentiation, you want open sets. You want open sets. Remember, for example, the definition of a what's that called? The definition of a directional derivative, probably, yeah, or not directional derivative, but just derivative in general. Right? The definition of a derivative in multivariable calculus requires you to approach a point from all directions. Right? If you don't have open sets, let's say if you include points on the boundary, then there's going to be certain direction in which that cannot be approached. Right? So the idea of an open set is that no point sit on the boundary. Okay, no, every point is an interior point. Every point has a little bit of a wiggle room to it. So here, the first sentence says, by a space of n dimension, we mean any set of objects which can be put in a one-to-one reciprocal correspondence. Reciprocal probably means bijective. Okay, so this part of the text requires a little bit of a translation into modern terms. It's a well-known concept, yeah, but the thing is, the definition was refined over decades, right? Because, well, Riemann introduced the notion of probably a Riemann manifold, or the prototype of Riemann manifold, but the definition that we typically use today was not available back then because topology was not even developed. Right? So the idea is you can build a function. Think of a job of the cartographer. Right? You look at a patch of Earth, right, and you try to represent that faithfully on a piece of paper. And there's better be a one-to-one correspondence between the region that you try to map and what's shown on the map. Right? So that's the idea. Of course, this is not the full or even rigorous part of the rigorous definition of manifold, but the purpose of this stream is highly computational. We're going to bypass largely the topological foundation of differential geometry and just work with coordinates. Okay, that's the basic skill we wish to develop, much like a high school student. Okay, we learn this material in an apprentice manner. Okay, so we still, like right now, my main objective is to be able to operate the machinery of tensor analysis proficiently. And then, of course, we'll later on dive deeper into the foundation. Okay, so just to keep things concrete and motivated. All right, so let's see. Let's continue. It says P be a point. P is a point. Okay, it has n components. So a point is an n tuple, x1, x2, all the way to xn. All right, and let's consider n equations, which is yi, and each is a function of all the xi's. I'm not quite familiar with the history of differential geometry. Okay, I'm pretty sure it's a fascinating story. Consider this. you have n equations, and they can be inverted, and assume they can be inverted locally. Assume invertibility locally. Okay, xi equals xi as a function of y1 all the way to yn. Oh, sorry, old habits die hard. I should use superscript, not subscript. If you come from traditional linear algebra and multivariable calculus, you would probably make that sort of little typo mistake as well. It won't mess you up, because later on upper and lower indices have actual meanings. Okay. Anyway, so yeah, just be very careful. Okay. Get used to the new notation. Okay. It says we assume these two equations are single-valued, well-defined. It is at once obvious that the point P can be put into correspondence with the n tuple. Y1 it's obvious that, yeah, this point P, x1 all the way to xn, can be put into correspondence with y1, y2 all the way to yn. I think what the author is trying to convey is the idea of coordinate transformation. It's also the definition of diffeomorphism, exactly. If you're talking about the definition of a smooth manifold, you need the notion of diffeomorphism. Main, I got an add in the main part here. What is the connection between manifold and arithmetic space? Again, the drawing you made. Well, a manifold, informally speaking, is an abstract space in which at every point its neighbor approximately looks like a Euclidean space. Okay, the principal word, okay, the operative word is its neighbor, so it's a local phenomenon. See here, see, this is a point on the manifold. The point on the manifold has a neighborhood that locally approximately looks like Rn, looks flat. So it's like, we know the Earth is curved. Hopefully there's no flat earthers in this stream. So yeah, the Earth, we know the Earth is curved, but from our everyday experience, the Earth looks flat. It's because our vision is constrained to a very small part of the Earth. And all those little neighborhoods eventually are patched together into a global object. And the global object, of course, in general looks nothing like Rn. But locally, this is fine. At every point, if you zoom in close enough, it looks flat. That's the notion of a manifold, basically. Of course, the technical definition is very complicated. Right? And because locally everything looks like Rn, you can introduce a coordinate system to describe to do geometry, basically. In fact, we will come to this point in the information geometry stream as well. Because in information geometry, the main idea is to consider probability distributions as points on manifold. So a statistical model can be seen as a curved surface, which is pretty cool. Right. And anyway, when it comes to comparing two models, it's a matter of calculating so-called distance. Actually, technically it's called divergence. It's not a real distance. Okay, it's called divergence. Actually, you know what? This evening we'll do information geometry. We'll introduce a notion called KL divergence, also known as mutual information. So that's the idea. So comparing two statistical models becomes an act of calculating something like a distance. So it becomes geometry. The whole enterprise of information geometry is to reason statistically, is to reason geometrically about statistics and machine learning algorithm. Just, in my opinion, pretty cool. Anyway, so here, let's continue. It says, Yes, differential geometry is made locally. Yes, of course there is a distinct field in differential geometry called global differential geometry. Okay, so sometimes it is possible to draw a global conclusion. It is possible to do that, but fundamentally, from a purely definitional point of view, differential geometry start from local behavior, even though sometimes global behaviors can be drawn, like how many holes does a manifold have? There are ways to answer this sort of thing. Yes, Christian said nailed it precisely. It's about being locally homeomorphic to Euclidean space. So homeomorphic means a continuous function with a continuous inverse. And diffeomorphism means it's a homeomorphism, but it's also differentiable, and its inverse is also differentiable. Right. So anyway, let's continue. So these are the more foundational notions in differential geometry. Okay, and in math, it's usually where specific examples were studied first, and then we try to generalize and give the most fundamental definition. So it's okay we don't start straight from the fundamental at the beginning. The KL divergence doesn't. It does. It satisfies the triangle inequality. It actually does. What makes it not a distance is because it's not symmetric. Okay. When it comes to metric spaces, it's not a metric. It's not symmetric. It's not symmetric. Okay. So we're trying. I think we're getting ahead of ourselves. Okay. But the metric needs to satisfy triangle inequality, positivity, and symmetry. So distance from A to B is the same with distance from B to A. KL divergence doesn't have the symmetry property, so it's not a metric for that reason. Okay, so so this is what the what information geometer called a dual asymmetry. Okay, called a dual asymmetry, which is quite fascinating in my opinion, but right now I cannot comment intelligently on that. Okay, but anyway, I strongly recommend you guys check out the book, Information Geometry and Its Application by Amari. And its applications by Amari. So it's probably the textbook on information geometry on the market that is most accessible. Okay. It assumes only linear algebra and multivariable calculus and some basic statistics. Okay. No differential geometry, no topology. It contains a more or less self-contained introduction to differential geometry. A big drawback of the book is that it has no exercises. Okay, so it has no exercises, so you have to be very, very diligent when it comes to checking your own understanding. Okay, so it only has main text, but it has no exercises. I listed a bunch of, actually two more texts at a higher level compared to the one by Amari in the stream description for information geometry. So if you guys are interested in literature, go check those out. Okay, so there you go. But basically, in Amari's text, which we will follow on that live stream, uses the language that we're using now. Okay, it uses the language of classical tensor analysis, much like a physics textbook on relativity. Okay, there's no heavy machinery of topology and formal manifold theory, etc. Okay, those things comes later. Okay, those things, once you have an idea of what the main intuition of the subject is about, those things can fall into place. Anyway, so let's continue with discussion. So here we have this n space, so-called m space, which really is a manifold. And I think the author is trying to describe coordinate transformation. So you can represent a point P using n numbers, x1 all the way to xn. And you can transform this set of coordinates into a new set of coordinates. Right? Very much like how we convert back and forth between polar and Cartesian coordinates. Right? For example, you have polar and Cartesian coordinate. So these are the coordinate lines, x and these are the coordinate lines for the polar coordinate. So theta equals constant and r equals constant. R equals constant gives you circles, and theta equals constant gives you rays through the, actually not rays, but lines through the origin. So you can convert between polar and Cartesian coordinate for all the points except the origin. So that's what we're trying to say. The Christoffel symbol. I'm not sure we will get into Christoffel symbols today. Okay, I'm not sure, but we will. I think we will get to the definition of tensors. So Christoffel symbol is also important in information geometry. Christoffel symbol is related to the Levi-Civita connection. Connection is a hugely important notion in information geometry. Connection. There are connections in information geometry that is not traditionally studied in classical differential geometry. So the study of information geometry actually drives the research of geometry itself, which is pretty cool. Anyway, so here it says n space, of which a p is an element, is also in a one-to-one correspondence with the set of a new coordinates y1 all the way to yn, so that we have a new coordinate system. The point P, the geometric object P has not changed, but you have a new method of attaching numbers to points. Right? So this formula, y as a function of xi, this is called a coordinate transformation. So this is called a coordinate transformation, and its inverse. Okay. Yeah. Don't take what I said as granted. Okay. I'm very much a novice. This is like a community-driven learning experience that I'm running right now. But yeah, go ahead and check out the literature I just referred to. Okay. Okay. And continue. No, I'm not a professor. Okay. So thank you, John Doe. But yeah, I'm just a guy trying to improve. Anyway, so that's it. Actually, that's it for this little short section on so-called arithmetic or vector n space. There you go. Okay. Perhaps vector n space is more modern nowadays. Arithmetic space is hardly heard anymore. Okay, and now we're going to get into the first geometric notion in our whole investigation, the new geometric notion, okay? Hopefully new for most of us here, called contravariant. Do we have any physicists in the chat? Contravariant vectors. Okay, so from now on, we're going to attach meaning to the upper and lower indices. And let's see how that's done. So let's consider a space curve. Okay, consider a space curve in Vn. By the way, I'm using the notation in the text. Vn stands for Rn. Okay, same thing. So space curve in Vn is xi equals, I do physics inspired MCMC. Okay, that's pretty cool. A different field of physics, statistical mechanics. You probably uses a lot of Gibbs sampler and whatnot. Now, xi equals a function of t. So this is true for all I equals 1, 2, and all the way to n. All right. So imagine this is a space curve. We'll give a concrete example shortly. Okay. So this is Vn, and you got a curve, like a trajectory of a particle. Undergraduate physics here. Awesome. So that's the space curve, and this is just a parameterized curve. Okay, and we restrict t to be greater or equal to alpha, less than or equal to beta. So, how do we describe the tangent vector? Well, the tangent vector is simple. The tangent vector is just the velocity, right? It's just the velocity of the curve. So let's draw that in the picture. So any instance, you got the velocity vector. This is a tangent vector. So the tangent vector all have components dxi over dt. Hi Mala. Thank you very much for joining the stream. So this is dxi over dt. That's the tangent vector. We'll do a more computational example shortly. Okay, so this is the tangent vector. And now let's consider a coordinate transformation. Like this one. Like this one. So you got y in terms of all the xi. So that's a coordinate transformation. Now introduce coordinate transformation. Yi as a function of all the xi. So y is a function of x1, x1 all the way to xn. Right? And then you got we can substitute all the xi's into this transformation. So yi as a function of t, y as a function of t is just yi of x1 of t all the way to xn of t. Right? Just substitute the space curve into the coordinate transformation, and you get this. So what is that? Well, this y of t is just the same curve, but expressed in a new coordinate. So this is nothing but the equation of the curve in a new coordinate system, in the y coordinate system. All right. So of course, it means the same curve, right? So it means the same curve. So the tangent vector should be the same, even though the numbers are different. So what's the relationship between these two sets of numbers? In the text it says, all right, let me just save me some writing. I'm just going to put down the text here. Okay, so that's the important piece of explanation, I believe. Certainly, the x-coordinate system is no more important than the y-coordinate system. We cannot say that dxi over dt is a tangent vector any more than we can say that dyi over dt is a tangent vector. If we consider all allowable coordinate transformations, we will obtain the whole class of tangent elements, each element claiming to be the tangent vector for that particular coordinate system. It is the abstract collection of all these elements that is said to be the tangent vector. So it's a very convoluted way to describe a vector. Oh, thank you. Thank you, PBJJ. Love you too. So, right? So the thing is, if we define a geometric concept like a vector using coordinate system, in order to be fair, we really are talking about a whole class of coordinate representation. Guys, sorry, I'm losing my voice. I don't know why. But anyway, so here, this is the dilemma we're facing here, right? So we wish to figure out a relationship between these two representations, dxi over dt and dy over dt. We now ask what relationship exists between the components of the tangent vector in the x-coordinate system and the components of the tangent vector in the y-coordinate system, okay, which it goes on to the next page, which I'm not writing. Okay, so anyway, and the answer is quite simple. Relationship. Okay, relationship between dxi over dt and dyi over dt. Right? The answer is just the chain rule. So dyi over dt, okay, using the chain rule. Right, so just in case we're clear what we're doing. So yi you usually draw this sort of dependency diagram in multivariable calculus a lot. So yi is a function of x1, x2, all the way to xn. And each xi is, of course, a function of t. Right? So the chain rule formula tells us, well, you represent each little line segment with a partial derivative or an ordinary derivative, depending on how many variables underneath it. Right? And then you sum up the contributions from each chain. So using the summation notation, this is nothing but partial derivative dyi over dx alpha, and then dx alpha over dt. There you go. So that's just the chain rule. That's the chain rule. And what would be the inverse transformation? Now, this is important, by the way, because this tells us how the tangent vector transforms. What's the inverse transform? Well, the inverse transform, let's try to derive that. Okay, the inverse transform is stated as follows. It's not proven in the main text, but we can easily derive that, I believe. So dx alpha over dt is the partial derivative dx alpha over dy. Oh, sorry. I mean, I should use I as an index. So on the left hand side, you got dxi over dt equals the right hand side partial derivative dxi over dy alpha, and then times ordinary derivative of dy alpha over dt. Right. So the first equation is by the chain rule. Of course, you can use the same argument to get the second equation, but let's prove the second equation from the first. It's a good exercise, actually. So let's imagine if you want if you already have the first equation and you want the second one. What you can do is you want to cook up with Kronecker delta on the right hand side. So let's call this 1. This is 2. Okay. Proof of 2 from 1. There's nothing more than multiplying the inverse matrix. So let's multiply 1 on both sides by, let me see, what do we want? So we want a Jacobian. So dx dxi dx so here, okay, first of all, on the left you got dyi over dt. On the right you got partial derivative dyi over dx alpha, and then ordinary derivative dx alpha over dt. So looking at this, the partial derivative of dy over dx alpha, we wanted to pair that with the inverse Jacobian. So should get a dx alpha. No, not dx alpha. Let's say dx. Let's use dx beta. Okay, dx beta over dyj. All right. dyi. So now the summation of I is implied. All right, so now we do the same on the left. You get dx beta over dyi. Right, we multiply dx beta over dy on both sides. This way, the left-hand side is unchanged, and the right-hand side is Kronecker delta beta alpha. And then dx alpha over dt on the right gets contracted. The index alpha is contracted, and you have dx beta over dt, which is exactly what we wanted. It's the same here. So we're done. Okay, so that's the proof of the second from the first. Okay, anyway, so now we're going to make the following generalization. So here comes the definition. It says any set of numbers, AI, which can be a function of x1, x2, all the way to xn. Any set of numbers, xi, AI, big AI, where I ranges from 1 to n. So that's an array, right? That's an array of n numbers. Any set of numbers AI which transforms according to the following law is called the components of a contravariant vector. Okay, let me write that down fully. Which transform according to this law, which is, let's write the new coordinates of big A as A bar, okay? The barred coordinate, A bar I, which is a function of the new coordinate x bar 1, x bar 2, all the way to x bar n. X bar n, all right, equals A alpha. A alpha, that's the original AI, okay? And its arguments are x1 all the way to xn. Okay, and then multiply that by the Jacobian, which would be the bar coordinate dx bar, okay, dx bar I over dx alpha. What you tried to show with the provable was the equivalence of 1 and 2. Well, in our exposition, I derived 1 from the chain rule, and then proved the second from the first. Markov, that's what we did. And of course, they are equivalent, right? You can start from 2 and then prove 1. They are equivalent, but what we just did is as I said, proof of 2 from 1. Okay, perhaps it's better to justify this step is just multiply dx beta over dyi on both sides of 1. Is what we did. Okay, so we notice that this law, you see, notice that the new vector is the Jacobian acting on the old vector. So we take that as our definition. Okay, I haven't finished writing that definition. So this, which according to the law, this one, this is, by the way, this is a very important equation. It's called 491. We box that. So we're well on our way towards tensors. So according to this law, under the coordinate transformation, are said to be components of a contravariant vector. Fancy names. Contravariant vector, okay? So this is a definition of contravariant vector. Okay, I think that's enough abstraction. We'll do an example. Okay, we'll finish reading the text. So here it says, after this definition, the text says, the vector is not just the set of components in one coordinate system, but rather the abstract quantity which is represented in each coordinate system by the set of components. Right. You can see mathematicians is probably revolting right now. A vector is an element of the vector space. It has nothing to do with coordinates. Whereas physicists define vector as the quote-unquote, you can think of it as the equivalence classes of coordinate representation, which seem a little bit inelegant from a mathematical point of view. But the thing is, physicists, they work with coordinates all the time. It's perhaps not such a terrible idea to define the quantity directly as a coordinate to save you the mental translation. Once again, as applied mathematician, our role is to be bilingual and to understand what each camp is saying. Right? So if you, yeah, exactly, the intuition is if you rotate your coordinate. Rotation is a specific kind of coordinate transformation. It's a very important one. But in general, here it can be nonlinear coordinate transformation, like from polar to Cartesian. The coordinates of a regular vector will rotate in the opposite direction that compensate. Right? That's the name of the that's the name contravariant. Okay, but enough of that. Enough of this abstract setup. Let's do a concrete example. Perhaps it clarifies everything. Actually, this is just to distinguish. Okay, these are examples that I included. Okay, it's not in the main text, but we will put a number after the example to indicate that's in the main text. Yeah, it's more general, but rotation is easy to visualize. Exactly, you're completely right. You're completely right. Actually, in a lot of tensor calculus textbooks, and not this one, a lot of dedicated tensor calculus textbooks, sometimes it's often common to first introduce coordinate systems that are constant. Okay, constant, or shall we say, introduce coordinate transforms that are linear maps. Okay, everywhere linear map, or so shall we say, it's the same everywhere. It's the same everywhere. So it's like rotations are such examples, and also other kinds of linear transformation, affine transformations are also examples. Okay, so basically, when you change a coordinate, the coordinate lines, the lines or surfaces of constant coordinates are still flat, and then it gradually moves towards a curvilinear setup. Okay, but here I think it's fine that we just do a curvilinear setup right from the start. Let's take a look at the following example. So you got just look at the circle. Okay, just look at the circle. So you have two coordinates, Cartesian and polar. The perfect setup to verify what we just did, Cartesian and polar. Cartesian coordinate xy. Okay, and you know what? Let's adopt the notation of x1, x2, and the bar coordinates. So the Cartesians are, say, Cartesian is x1, x2. And you also got the polar coordinate, which is x bar 1, x bar 2. Right. So, yeah. And now we consider a circle, unit circle. Unit circle. So first of all, actually, you know what? We want the Jacobians and whatnot, right? So we'll leave space for that, and then we look at the circle. The circle in two coordinate system. So this is two coordinate system, which is familiar to all. And just going to verify what we just did is valid. All right. So the two coordinate systems are Cartesian and polar. So how do you convert from Cartesian to polar? Well, it will be, let's draw a picture here. So this is the point x1, x2. Actually here, x1, x2. All right, this is the point. And then the length is x bar 1, that's r basically, and the angle here is x bar 2. So x bar 1 is the square root of x1 squared. Okay, I'm going to use bracket to indicate squares. Okay, so this way there's no confusion about the indices. So this is x1, and x2 is, x bar 2 is the inverse tangent of x bar 1 over x bar 2. At least locally this makes sense. Right. So that's the transformation from x1, x2 to x bar 1, x bar 2. So what would be the inverse? We'll just keep that now, okay? So we're probably going to use the inverse transformation somewhere down the road. So let's just calculate that for convenience. So x1 is, of course, r cosine theta, which is x bar 1 times cosine of x bar 2. Yeah, I suspect this live stream will attract some physics folks here, because this is still the workhorse of physics. x2, perhaps fewer mathematicians. x2 is x bar 1 times the sine of x bar 2. So that's the transformation and its inverse. And now we're ready to describe the circle. Right? The parameterization of a circle. Here we go. The unit circle. To make things as simple as possible, so this is a unit circle in a plane. All right. We got the circle. Okay. Radius is 1. So x1 is cosine of t. x2, unbarred coordinate. Okay. x1 is cosine of t, and x2 is sine of t. Simple. Is x bar 2 defined itself? X bar 2 is the angle, the polar angle. Tx, x bar 2 is the angle. It's like theta. It's the usual notation for polar coordinates theta. I'm just writing x and x bar to conform to the notation, the definition. Because that's the general notation. Okay. We're treating the unbarred coordinates as regular Cartesian coordinate and the barred coordinates as polar coordinates. Okay, and what would be the description for the same circle, right? The same unit circle, but in the polar coordinates? Well, you can use the transformation. It's not difficult at all. You just plug in the formula. Okay, x1 bar is what? Is the square root of cosine squared plus sine squared, which is of course 1. So x bar 1 is constant 1. And that's geometrically obvious because x bar 1 is just the radius. On the circle, the radius is constant 1. Yeah, from Cartesian to polar. This is from Cartesian to polar. And this is from polar to Cartesian, the other way around. Right? And remember, the t, the constant, sorry, not the constant, but the parameter t has a meaning here. Okay. T is this angle. Let's see, this is x1, this is x2. So t has a meaning here. And you can just read from the picture that x bar 2 is just t. Of course, x bar 2 in general is multiple valued. But we're just going to define x bar 2 equals t. It works. Okay, and a little comment here, because earlier we treated the parametric curve to take equality at the endpoints. But here, it's not really a coordinate representation globally because at t equals 0 and t equals pi, there's ambiguity. It's not a diffeomorphism, basically, because the function is not injective. But that's a small problem, okay? If we're super serious about the rigorous definition of differential geometry, we'll have to worry about this, Okay, in which case you have to what we call in differential geometry represent the full circle using two coordinate patches. Because in formal differential geometry, you have to define the correspondence with R1 in this case, with Rn, which is in this case an interval, using open set. So in formal differential geometry, this is actually not allowed. You only use open sets. Okay, but here we're not going to be super formal. Just a reminder here, because this map fails to be injective. All right, but that doesn't matter. So everything is considered locally. Okay, everything is considered locally. So now let's verify this transformation law. Okay, what's the tangent vector? What's the tangent vector? In fact, what's the tangent vector components? Right. We've been talking about components. I'm going to use the physics notation. Let's write x1 dot. Okay, x1 dot is minus sine of t. And x2 dot is a cosine of t. That's the tangent vector component in the Cartesian coordinate. And now let's do the same differentiation thing. X1 bar dot, okay, x1 bar dot is 0, and x2 bar dot is 1. Okay? So according to the transformation law, what should we satisfy? Okay, what should these two tangent vectors satisfy? It says we need to verify the law, okay, which is x bar dot 1. X bar dot 1. Here you see in the definition, I is a free index. Right? I is a free index. The bar component is the unbarred coordinate, so that's x bar alpha, and times what? Times the Jacobian, times the transformation. So you got d x bar 1 here, dx bar 1 over dx alpha. Okay, I'm actually just going to, you know what, just to save some scrolling back and forth. That's why in universities you need a room with 4 blackboards at once, right? Because this is too small for showcasing math. All right, so you see, so we need to verify that, and also when I equals 2 as well. So you need x bar dot 2. You need x bar dot 2 to be x. No, this is nonsense. So here I added a bar here. You don't need bar here. Can I delete that? Yeah, thank you very much. So this is x alpha dx bar 2 over dx alpha. See how that works? I is a free index. It runs from 1 to 2. Okay, so we need to verify that. All right, so let's calculate the Jacobian. Let's calculate the Jacobian. In fact, you know what? Let's put it right under the coordinate transformation. Let's do that here. Let's calculate the Jacobian. So once again, this should be familiar from multivariable calculus. So you got dx bar 1 over dx1, dx bar 1 over dx2. I'll write it as in a matrix format, and then dx bar 2 over dx1, and then dx bar 2 over dx2. Okay, differentiation should be straightforward. It should be straightforward. So I'll just do the scratch work underneath and then erase that and just put the results here. Okay, so differentiation, the first one, dx bar 1 over dx1 looks like 1/2 times x1 squared plus x2 squared, quantity taken minus 1/2 power, and then times 2x1. So this is just x1 over the square root of x1 quantities. No, you see, I messed up the upper and lower index. This is so tempting to write lower index because you've been doing that for years. x1 quantity squared plus x2 quantity squared. Okay, so this is just x1 over x1 bar. X1 bar. X1 bar. That's just x1 bar. So here, basically x over r. That's basically x over r. So yeah, you have x1. No. Why do I keep making the same mistake? Old habits die hard, man. Upper index, upper index, upper index. Okay, x1 over x1 bar. Like just regular differentiation. And the second component, well, dx1 bar over dx2, similarly, would be x2 over x1 bar. And that's it. Okay, so I'm going to erase that. And then do the second differentiation. All right, so hold on a second. This looks nonsense. My goodness, why did I add bar here? Why do I randomly add bar here? Sorry about that. x1 over x2. Yeah, x1 over x2. So dx2 bar over dx1. Inverse tangent derivative is 1 over 1 plus x1 over x2 quantity squared, and then times 1 over x2. All right, use the chain rule. So this way you get x2 squared over x1 quantity squared plus x2 quantity squared over 1 over x times 1 over x2. So one of the x2's cancel, so you just get x2 over x1 squared plus x2 squared, which is exactly just x1 bar squared. Right? So you put a x2 over x1 bar squared downstairs. Okay, and then the last derivative x1 bar. Yeah, inverse tangent of shit. Vernon, you're right. My goodness. Yeah, why am I so sloppy today? Sorry guys. This is a disaster. This is a disaster. All right, redo everything. Redo everything. Okay, sorry. Yeah. Vernon, you're completely correct. Thank you very much. X2 over x1. Jesus. x1 quantity times minus x2 over x1 squared. Okay? So that's a minus sign, x2 over x1 quantity squared, x2 quantity squared. All right, so that's minus x2 over x bar 1 quantity squared. Okay, yeah. I think, yeah, because we did the other differentiation earlier, this should be x1 over, yeah, this should be x1 over x bar 1 square, x1 bar square, okay? Yeah, this should be that. Okay, so we represented all the matrix element. We calculated all the matrix elements. So there's that. Because even to this day, I hate working with square roots and fractions. Okay. All right. So second Jacobian, the inverse Jacobian. All right. So this should be easier. So x dx1 over dx bar 1, dx1 over dx2 over dx no, it's just still dx1 upstairs, x1 upstairs. All right, dx bar 2. Now you have x2 over dx bar 1, dx2 over dx bar 2. Right, that's the inverse matrix. And we'll verify the product is indeed identity, okay? Just to check the calculation. So the first component, of course, that's just cosine of x bar 2. Okay, and then you get minus x bar 1 sine of x bar 2. Okay, nice. Differentiate x2 with respect to x bar 1 gives you just the sine of x bar 2. And the next differentiation is x bar 1 cosine of x bar 2. Okay, so multiply the matrices to see if that gives you identity. It better be, right? So yeah, let's now verify the dx bar I over dx alpha times dx alpha over dx bar j, okay, is the delta ij. Basically, you should get an identity. Okay, so here, all right, do the matrix multiplication. There you go. Okay, let's see what we have here. Here you got x1, the first element, well, that's x1 cosine of x bar squared, oh sorry, not x bar squared, x bar 2 over x bar 1 plus x2 sine of, hold on a second, that makes sense here. The hell is that? I thought this one should cancel. I thought this one should be 1 or something. Oh yeah, that's right. That's right. Because x1 over x bar 1 is cosine. That's what you get, a cosine square. This is a cosine square and a sine square. You add them up and you get 1. Nothing is wrong. Okay, nothing is wrong. Yeah. Okay, so this is just 1. So yeah, let me just erase that. This is just 1. Okay, so this is 1. And the second element, okay, you do this, right? The second element would be x1 minus x1 sine of x bar 2 plus x2, well, x1 cancels. Hold on a second. Hold on a second. Is that right? Actually, no, that's just not. This is still, there's problems. I wish you know what? Guys, I wish I kept the x and y r theta, because that helps me mentally. All this x1, x1 bar stuff messes me up. Okay. So how do you do the second element? So that's minus x1 sine of x bar 2 plus x2, right? x2 times cosine of x bar 2. How does that cancel out, huh? How on earth does that? Well, look at the picture. Sine of x x bar 2 is x2 over x1. Cosine is sine is x2 over x1 bar. My God, the scripts are all over the place, man. x2 over x1 bar. And cosine is, look at the picture, is x1 over x1 bar. So you see they cancel out. So we're good here. Thank goodness for that. Okay, so that's 0. So that's 0. So that's verified, okay? It's very mechanical. So here, and the second one, the second row is, here you got minus x2 over x1 bar quantity squared times the cosine of x bar 2 and plus x1 over x bar 1 squared times sine of x bar squared. Sorry, not x bar 2. All right, so sine of x bar 2 is x2 superscript x2 over x bar 1. Cosine is x1 over x bar 1. So you see they do cancel. All right, so this is 0, as it should be. As it should be. So here you got the 0 here, and the last one you get the second row, second column multiplying together. So the minus sign canceled out. You get x2 x1 sine of x bar 2 over x bar 1 quantity squared, okay, plus x1, okay, over one of the x bar 1 cancels, x bar 1 times the cosine of x bar 2. So the cosine of x bar 2, as we mentioned, is x1 over x bar 1. Right? Yeah. And here the sine is what? The sine is x2 over x bar 1. How does that cancel, huh? Oh, actually, one of the x1 bar cancels. Actually, I messed up the algebra again. Oh my goodness. I wish I kept everything in terms of r and theta. This way it helps me mentally, but it will be harder to tell whether the transformation law still holds. So yeah, I made a compromise there. So the first product would be x2 over x1 bar. Yeah, and then times the sine. The sine, as mentioned, is x2 over x1 bar. So you see, the bottom part are all x1 bar squared. On top, you got x1 squared plus x2 squared, which cancels out exactly. So once again, this is 1. Whew. Okay. Praise the Lord. Everything works out. Okay, there you go. So this is the identity matrix, indeed. Okay, so you got the Cartesian polar coordinate, the Jacobians, verifying their inverse relation, unit circle, tangent component. Now we can verify that. Okay, cool. So, well, so what does this say? Well, expand that in the summation notation. So x explicitly. So you expand the summation notation explicitly. So x1 bar dot should be x1 times, and by the way, these x's should be evaluated on the curve. Should be evaluated on the curve because only the coordinate on the curve matters. So, and here you get x bar 1 over dx1 plus x2 unbarred coordinate times dx bar 1, okay, over dx2. Okay, this is what you need. And here, the second equation would be x bar 2 x1 dx bar 2 over dx1 plus x2 dx bar 2 over dx2. Looks okay. Yeah. So everything seems okay now. All right. So we need the Jacobian on the circle. So on the circle, what are these Jacobian elements? On the circle, dx bar 1 on the circle. Let's write down the Jacobian. Okay, we want bar over unbar. So that's the first matrix. So we want this matrix. Let's put it here. On the circle, what happens? Of course, on the circle, the radius is 1. On the circle, the radius is 1. So basically, you substitute. x1 is just cosine of t. X bar 1 on the circle, you get, okay, x1 is cosine of t. x2 is sine of t. x1 bar is constant 1. All right, so the first entry is cosine of t, second is sine of t, minus sine of t, and you get cosine of t. There you go. So you can look up these entries precisely. All right, so what's x? Let's call this, let's call this equation 1, okay? Equation 1, equation 2. Let's verify 1. What is x? What is x? The x1 bar dot. What is x bar 1 dot? Here, x bar 1 dot is 0. Right here, x bar 1 dot should be 0. This thing should be 0. This thing should be 0. So we evaluate the right hand side and see if that actually vanished. Let's put a 0 here. Equals question mark. X1 is cosine of t times dx1 bar over dx1, which is cosine of t. Uh-oh. Plus x2, that's sine of t, times dx1 over, I think something is wrong here. dx1 bar over dx2, this one, the sine of t, so that's 1, huh? It's messed up. So here, I don't know why. So this should be correct, but somehow it's messed up. Look at the transformation law. Recheck. Bar on top, unbar at the bottom. bar on top and bar at the bottom. So this is what we wanted to verify. X bar 1 should be 0. So this looks like what? This looks like the first row. Is this a first row? Can we can we repackage this into matrix form? Can we repackage 1, 2 into matrix form? Into matrix form, this should be x1 bar dot, okay, x2 bar dot together equals dx1 bar over dx1, dx1 bar over dx2, dx2 bar over dx1, dx bar 2 over dx2 times the oh, it should be tangent vector. I was stupid. My goodness. Why did I miss the dot here? It should be tangent vector, right? If you don't add the tangent vector, it's a radius vector. Of course that doesn't match. Okay. Yeah, that's the problem. Okay, you know what? And let's rewrite this in a matrix form and then just verify the matrix form. Okay, it's equivalent. X1 dot, x2 dot. That was a mistake. Okay, that was a mistake caught. I forgot to add dot on the right hand side. Okay. All right. All right. So verify that. Okay. So let's verify 1, 2 together becomes this, which is equivalent to the matrix form. Where do I see the Jacobian and the contravariant vector definition mean? Jacobian here. So let me just change this real quick. Okay. Where did you see the Jacobian? Because in the definition, things are written in a component-wise fashion. Yes, we're verifying the contravariance. Exactly, we're verifying 491. Right? So here, we're verifying that the tangent vector of this unit circle satisfies the contravariance law. Right? This is 491. This is 491, which is this, and this. They all mean the same thing. Yeah, I just wrote that. Exactly. All right, so let's go. So on the left, you should get 0 and 1. All right, so you should have 0 and 1. Let's see if that actually works. Okay. All right, so you should have 0, 1 on the left. The Jacobian matrix cosine of t, sine of t, minus sine of t, cosine of t, multiply with what? With x1 dot, x2 dot. Well, x1 dot is minus sine, x2 dot is cosine. So now it should work. Indeed, 0 and 1. Hooray! It works. Okay? The contravariance law works for the tangent vector for the unit circle. Okay, this is our first step towards tensors. It's our first step towards tensor because tensors will have more than one indices in general. And the contravariant tensors also satisfy this property. So if you see a tensor with all upper indices, it transforms like this. It transforms according to the forward Jacobian, if you can call it that way. And if you use lower indices, then it transforms according to the inverse Jacobian. Okay, so we're getting ahead of ourselves. So basically, let's come back to the main text. Okay, so yeah, the text says we immediately see that the law of transformation for a contravariant vector is quote-unquote transitive. So what does that mean? Okay, so let's continue. This is the end of our example. Proposition. It says the law of transformation for contravariant vectors is transitive. Okay, meaning, hi MD. So what do we mean by this is, let's say you transform the coordinate twice. Seems to be that way. Okay, so let's say if you transform it once, you get a bar I equals a alpha. Oh, old habits die hard. Upper index. The component of a contravariant vectors uses upper index. Tensors in any mathematical objects that could transform nicely. Yes, exactly. Yes, completely right. So these are the components transform according to a particular law, and tensor vectors themselves are geometric invariant. Right? It's just like the tangent vector is an object on its own. Right? The way you measure it should be related in a particular way. So x a bar I equals a alpha dx bar I over dx alpha. So that's the first transformation. So imagine you have coordinates from x i's to x bar i's. Coordinate transformation. Okay, so you from xi transform to x bar I, and then you do it again. You get x double bar I. So hard to define with what tensors are. Yeah, the thing is, our understanding of tensors will progress. Just like our understanding with vectors will progress, right? In high school, you learn vectors are arrows and sticks, the direction and magnitude. And then you learn, oh, vectors is just a finite list of numbers. It's an n-tuple. And then you come into linear algebra, abstract linear algebra, and learn that, oh, vectors are elements of abstract vector spaces. A similar trajectory will happen to us when it comes to tensors, okay? So our very first, never understood the physicist tensor from a point of view of tensor product. You can't show actually their equivalent. I remember I showed that like 10 years ago. They are the same thing. They're the same thing. The mathematician's point of view is the same as the tensor. I don't know it as a physicist one, right? Vernon, I mean, once again we're getting ahead of ourselves. Vernon, if you've seen the mathematician definition of tensors, you probably define it as a multilinear map. It's linear in each component. It's a multilinear form, actually. It means it takes a real value, and the function is linear in each component, holding all the other arguments fixed. Right? That's called multilinearity. You can derive these transformation laws from multilinearity. I think I managed to do that when it was 10 years ago. I remember I did that before. So really, physicist definition is implied by mathematician's definition. Crucial flow research. Physicists view that, say, a tensor transform as a tensor. This definition is self-referential, so mathematicians don't use that. Well, it transforms according to this formula, right? There's nothing wrong with that. There's nothing wrong with that. There's no circularity here. It's just that from a mathematician's point of view, the so-called orgy of indices is really obscures the geometric insight. But the thing is, in physics and engineering, you work with these concrete representation, right? However, in mathematics, you often want to consider the set of tensors as a whole. So imagine carrying all those indices. It's just different perspective and different priorities. The definition is a nightmare, exactly. So that's why I'm not jumping into like the next definition, right? So I gave the definition of a contravariant vector motivated by how tangent vector works, right? So here we have a concrete example of how tangent vector transform, and then abstract that into the definition of contravariant vector, and then use a concrete curve, a circle. So hopefully everything we've done now can help us get a hold of this definition. This is the definition of contravariant vector. A contravariant vector has component that behave this way. Okay, so that's the physicist definition. All right, so let's continue. Here, the proposition says the law of transformation of a contravariant vector is transitive. What do we mean by that? Well, imagine we have two consecutive coordinate transformation from xi's to xi bar and to xi double bar. Okay, so this means, the proposition means we'll do this law essentially twice, right? So a double bar I. Okay. Do you have access? Yes. Yes. Yesterday's notes was published. Not published, but it's in the. If you go into the stream, I mean, not all. I'm still in the process of organizing everything, but yesterday's notes are, at least recent streams have their notes published. Okay, I should do this for all the streams earlier. Yeah. So yeah, yesterday's stream, basically this one here was uploaded as a PDF. Well, except for the last example, which we did today. So this will be uploaded. I put all my notes so far in, as far as this subject is concerned, in a folder on Google Drive, and the link is in the description. Everyone is the link. The link is in the comment. You click that, you can see it, hopefully. Crucial Flow says, personally as a mathematician, I don't invoke calculus of tangent spaces to define tensors. I think tensors are algebraic. Yes. Yes. Tensors has nothing to do with calculus. Exactly. You're completely right. You're completely right. Guys, if you are interested in what Crucial Flow research is saying, I have an excellent resource for you to check out. This is on MIT OCW. Okay, I'll put it in chat. So if you guys can't wait to see the mathematician's perspective, go see that. Okay, so it's called Analysis 2. Analysis 2, here. Yeah, right here, this one. Analysis 2. In particular, there's a set of notes on multilinear algebra. Readings. Is it reading? Yeah, supplementary notes on MLA, notes on multilinear algebra. This one right here. Okay, so this one. So this is, you know, mathematician will love this. Okay, go ahead. You start from the abstract linear algebra, the dual space, and then proceed, exercise it, and define tensors this way, as a multilinear form. Right. So Crucial Flow research. Are you happy right now? This is a modern definition. There's no calculus. Okay. You're completely right. It's an algebraic object. It's an algebraic object, right? So, but the problem is, for applied scientists, it's difficult to see why this is useful. Why should we give a damn, right? So, and how does this connect to existing literature, right? So, it's so amazing that there are different approaches to mathematics. Yeah. So you see, by the way, this whole course is recommended. Okay, this whole course is highly recommended. Okay. So, it's just consider this as vector calculus on steroid. There you go. Okay, it's in the link. The link is in the in the chat now. Go ahead and check this out. Analysis 2M from MIT OCW. Okay, and in particular, the notes on multilinear algebra is this one. In particular, okay, this is a note on multilinear algebra, the treatment of tensors from a modern algebraic perspective. It is absolutely an algebraic object. Okay. The problem with starting your discussion on tensor from this perspective is it is difficult for applied scientists to grasp. Okay, how is this even helping me, right? Okay. What I'm saying is the definition of tensor from this right here, so in this second section, it can imply the physicist's definition. Yeah, it doesn't matter. Like, the nice thing about mathematics is that you can always write your own text on the same subject. Okay, and there's no accusation of plagiarism as long as you credit. Right? This is what mathematicians do. It seems kind of funny to outsiders. Why do mathematicians keep writing books about the same thing, right? So it's like, why do we even need a new books on calculus anymore? Right? But it is helpful. It is helpful. The math is a conversation. It's a conversation. So do not think of writing book on old subject useless. Okay. Euclid's geometry. In Euclid's book on geometry, most of the theorems are not discovered by Euclid, but what he did was absolutely monumental. He axiomatized the subject. Right? Even though individual results were, many of the he of course do have his own results, but many of the individual results were discovered way before him. So in a sense, it's mostly old math, but like you know the argument, right? It does not matter if somebody else has already written a subject on X, right? So anyway, so let's close this up and continue. Yeah, it's an old subject, but most people still don't know it. Yeah, it is completely true. It's still, there's a lot of confusion about what tensors are, right? So anyway, let's continue. Okay, so the proposition says the law of transformation for contravariant vectors is transitive. Imagine you have two consecutive transformations, so let's write down the law of transformation twice. This is the first transformation from unbarred to barred coordinate. And then you have one bar to double bar coordinates. Okay, so a double bar I equals a bar alpha dx double bar I over dx bar alpha. Okay, so let's think about how do a double bar and a unbar relate. Okay, so there you go. You get, let's try to do the substitution. A double bar I, let's substitute a bar alpha, so a bar alpha, well, you have to swap I to alpha, but once again, the summation index alpha has to be changed, so let's write a beta. Okay, let me do this a bit slowly, okay? So you need a bar alpha. You need a bar alpha to do the substitution, but you cannot directly substitute alpha without changing anything else. So we change the summation index alpha to beta. That's it, okay? A beta dx bar alpha over dx beta, yeah? This is a bar alpha, all right? And then times the second Jacobian, which is d double bar I over d single bar alpha. Right? Notice what happened. You have a Kronecker delta, I believe. Actually, that's not Kronecker delta, isn't it? That's not Kronecker delta. That's just a new Jacobian. It's just a new Jacobian because, hold on a second. Hold on a second. What is going on? Yeah, alpha is summed over. Alpha is summed over. What's your thoughts so far using textbook with streaming? What's your thoughts on fair use? This one is copyrighted, so I do most of the writing myself. Okay, for measure theory, I use extra, which is completely in public domain, so I just show the book. Okay, so here, if let's say if I encounter a paragraph with heavy writing, I'll do the screenshot and post it on screen, and I'll delete it. Hopefully, and I will of course add our own commentaries. So I think I'm pretty safe when it comes to that. Okay, so this book by Lass is copyrighted, and it's difficult to obtain a physical copy nowadays. Okay, but it's so great, man. It's so great. The other chapters are all also amazing. Okay, it is such. Okay, so basically, guys, this is let me just show you the list of content here. Okay, so this is the list of content in my PDF reader. If you search the book, it will show up on Google. Okay, but I will not show it on my channel. You see, start from algebra vectors, differential vector calculus, differential geometry in the sense of differential geometry of curve and surfaces. So this is classic differential geometry in curve and surfaces, Gaussian curvature and whatnot. Okay, integration. This is the usual stuff found in vector calculus, Green's theorem, Stokes' theorem, Gauss's divergence theorem, and all of that. Static and dynamic electricity. So this is electrodynamics, electrostatic and electrodynamics, Maxwell's equation, that sort of thing. Mechanics. This is the part where we discuss classical mechanics, rigid body, including rigid body, hydrodynamics and elasticity, fluid stuff. You see, it's all integrated. Okay, so everything has a purpose here. Once it's introduced, it's then immediately applied. It's not like in some mathematical, so applied mathematics textbooks that you spend so much time in theory building, and when it comes to application, it feels like an afterthought. Okay, so here, see, once you introduce the differential vector calculus, it's immediately put into use for studying 2D and 3D curve and surfaces. So that's pretty cool. And right now we're in chapter 8, Tensor Analysis and Riemannian Geometry for the applications of tensor analysis, including Einstein's gravitational theory. So this is such a great book. I like it a lot. Okay, it was used as a reference book for my own course in uni for vector calculus, but we mostly used professor's lecture notes, and we had no time discussing much of the applications. So anyway, that's the book. Strongly recommended, by the way, if you can't tell already. So here, we're doing this substitution, and what is that? Well, remember, notice that this is just a chain rule, so you just get a beta and x double bar I over dx beta. So that's the relationship between the coordinates of a double bar and a. What do we search in Google? It's the text. You see, go to the stream description. Vector and Tensor Analysis by Harry Lass. Okay, I'll put it in chat again. It's old, but it's gold. Okay, it's in the same series with Baby Rudin and the L4's complex variable course. Both are considered, among others, okay, both are considered just well, I don't need to say anything about Baby Rudin anymore. So basically, yeah, I don't know why this book is perhaps because of the antiquated language, right? But the content is still amazing. like the one we've seen earlier, the arithmetic n space. Pretty much nobody uses that term anymore, but still, the mass itself is timeless. Anyway, let's come to the next component. So here it says, let me just put the this, because there's some heavy writing here. Let me just put it on the screen. All right, so there you go. Is that if the components of a contravariant vector are known in one coordinate system, then the components are known in all other allowable coordinate system by 491. So 491 is this particular definition. Yeah, that's 491. You can use 491 to do the coordinate transformation. Okay, so that's understood. A coordinate transformation does not give a new vector, of course. It merely changes the component of the same vector. We thus say that a contravariant vector is an invariant. It's a vector itself, okay, not the components, of course. Right? The contravariant vector is an invariant under coordinate transformation. Right, so modern geometry and also physics, right, are centered around the notion of invariant. A different kind of geometry has different invariants. So, invariant under various coordinate transformation. An object of any sort which is not changed by transformation of coordinates is called an invariant. All right. So, okay, so let's just put it here, and then we continue to the next example, this actual example in the text. All right, so let's highlight that. We say a contravariant vector is invariant under coordinate transformation, okay? Let's go. Now let's continue. Example 11. So in the last section we were at 11, example 10, okay? Sure, this is example 11. Example 11 says, here, it says let x, y, z, big X, big Y, big Z be components of a contravariant vector in Euclidean space in E3, okay? Let's just call it E3 or V3. Use V3. Previously we used the notation V3. And for an orthogonal coordinate system. For an orthogonal coordinate system. These are components of a contravariant vector for an orthogonal coordinate system. I'll draw a picture for that. All right, so here you have the three axes, x, y, and z. Okay, and write ds squared equals to d little x squared. Why are we all of a sudden using little x? I'm not sure. Okay, so let's just continue. Dx little squared, dy little squared. That's called the line element. dz squared. Okay, just the distance formula. Yes. And then it says the components of this vector in a polar coordinate system, which really is the cylindrical coordinate system. I'm going to use the term cylindrical, okay, because to avoid confusion, because polar coordinates is nowadays only reserved for 2D now. Cylindrical coordinate. So cylindrical coordinate system has three numbers: big R, big theta. Okay, big theta would be, let me just write it this way, big theta, okay, and big Z. So if we are to draw the constant coordinate surfaces, in this case will be surfaces, what would that look like? So constant Z would be a horizontal plane, like so. So this is constant z. What's constant r? Well, constant r, that's the cylinder, so hence the name. Okay, let's draw the constant r surface. This is a constant r, it's just a cylinder. And what is could you give some counterexample, me? Because, sorry, I didn't read your comment. So could you give some counterexample? Because the first side, for me, it seems that we're doing the same coordinate transfer vector should be the same. Later on, you mean vector that does not behave this way, right? So Marco, are you talking about vectors that do not behave this way? So you're talking about, by counterexample, do you mean a 1D array that does not obey this law? Is that what you're asking for? If so, later on we will see the gradient vector in calculus does not behave this way. So the gradient vector in multiple calculus is not the same. It's not of the same nature as, say, a tangent vector. The gradient vector is what mathematicians like to call it a linear one form. Is a linear one form. So in a gradient vector, you don't use the forward Jacobian. Instead, you use the inverse Jacobian. So that's another class. So that would be quote unquote perhaps a counterexample. So it does not work this way. Not all 1D arrays transform this way. So that's the second class. Okay, so in multivariable calculus, we identified gradient as a vector, as a like in the picture, the gradient looks like, okay, it's perpendicular to the level curve and whatnot. It's pictorially seems to bear little distinction, say, compared to tangent vector. But really, gradient are another class. Okay. They're covariant, not contravariant. But we'll get to that. Okay. So here we're just doing more examples. All right. So this is the constant zeta surface. Constant zeta surface. So what's the relationship between Cartesian and cylindrical? Well, from the picture, we can just we can see that r is the square root of big X squared plus big Y squared. Once again, this is local transformation. Big theta is the inverse tangent of big Y over X. Thank you, Vernon, again, because I wrote big X over Y first. And finally, Z is what? Okay, Z is just Z, no difference. It's the same. Okay, so here hold on a second. Okay, this is what the text says, and I'm a little bit confused here. Okay, guys, help me out here. I'm a little bit confused, so what's going on? This is what it says. Big R is X times, why is that? Is there a mistake? It says the components R theta Z are not projections of the vector big A onto the R theta Z directions. However, if the theta component is given in the dimension of the length by what? Okay, I'm a little bit confused. Okay, so here we're trying to describe a vector using two coordinate system, x, y, z, and r theta z. is this transformation wrong? Here, you see the transformation little for little theta. What's the difference between big and little? Well, here it says little ds squared is little dx squared plus little dy squared plus little dz squared. So what are these? So r dr dx dr dy. Oh, I'm so sorry. I'm so sorry. These aren't coordinates. Big X, Y, Z, and R theta. They aren't coordinates. Okay. These aren't. These are the components of vectors. The components of vectors. My bad. My bad. My bad. So basically, okay. Let me rewrite this. Okay. Let me rewrite this. This is not a cylindrical coordinate system, but rather. Let me actually reorganize everything, just like in the previous example. Okay, so I think that will be a little bit better. Okay, so guys, I think this is not a very good presentation, what I just did. Sorry about that. So let's say consider, start over, okay? Consider a contravariant vector. Consider a general contravariant vector. With components in two coordinate system. With components big X, big Y, big Z in Cartesian. In Cartesian coordinate system, which is little x, little y, little z. So that would make sense. Yes, I think now I got it. Big X, big Y, big Z are components of vectors. They're just numbers, okay? They're just numbers. They're just numbers. So imagine you, once again, let's use the space curves analogy. You have a curve in 3D space. And actually, you know what? Actually, I don't think we have time to verify that, but you can verify this transformation law here for the tangent vector of a helix. How about that? So helix is a 3D curve. You can do kind of the same process we did for 2D. Okay, and I think much of the calculation would be identical actually. So consider once again, you might consider a contravariant vector. For example, a tangent vector. Like the velocity vector. Right? And you can describe it in Cartesian coordinate system, little x, little y, little z. And the result of that is the three components, big X, big Y, big Z. And you can do it in the polar coordinate or the cylindrical coordinate as well. And you get three components, big R, big theta, and big Z. Big R, big theta, big Z, and in the cylindrical coordinate. Cylindrical coordinate system, little r, little theta, and little z. Okay, so I'm going to erase everything here. So this is irrelevant. Okay, so let me just keep what I can keep. Okay, so in diagram, these aren't big x, y, z anymore. Okay, these are little x, y, and z. They describe points in the 3 space. And the green ones, the green surfaces, these are okay. Constant little z. Constant little z. This is constant little r. Constant little theta. Okay. Okay. So this is what we're dealing with. Then what does? Okay. Then what does 491 says. Like, what does this definition say? What does this 491 say? Okay, Marco, you're unhappy. Are you still unhappy now? Because I was confused. Okay. Basically, this is what 491 says. Okay, recall 491 says, how do you convert big X, big Y, big Z to big R, big theta, big Z? Right? 419 says this. Okay, for that I'm just going to use this. Okay, I'm just going to use this. Okay, to save time. So this is the transformation. This is 491. Right here we assume we have a contravariant vector, and the three components in Cartesian and cylindrical coordinate as such. Yes, so x, y, z are vector components. Are vector components, exactly. Yeah, your brain hurts, I know, right? This is a confusing topic. Okay, so what we did here in our homemade example, okay, this circle example, you can think of x dot as big X. Okay, x1 dot as big X, x2 dot as big Y. They two together are the components of the tangent vector in Cartesian coordinate. Okay, and 0, 1 together are the components of the tangent vector, the same tangent vector in polar coordinates. So you can imagine this is x bar 1 dot, okay, this thing as big R, and this is big theta. So is that clear now? So if this is still unclear, we can do another example using a helix. What's a helix? So everything has their meaning. Okay, so consider tangent vector of a helix. Perhaps the most widely used toy example for 3D curve. Consider helix, tangent vector of helix. There we go. Okay, like this. X, little y, little z. Okay, so what's the curve like? The helix. Okay, let's still do the same business. Okay, so you have Cartesian, polar, not polar but cylindrical. Okay, I want to make this crystal clear. Okay, so you have Cartesian and cylindrical, Jacobians. What else did we did earlier? We have Jacobian. Okay, we did that verification. We can skip that. Helix. What is helix? Helix. Tangent vector. And you can verify. Verify 491. The transformation law. Law of transformation for contravariant vector. Okay. So Cartesian coordinates is x, little y, little z. Cylindrical is r, c, theta, and little z, all right? Okay, first of all, we need the transformation, not the Jacobian. Okay, how can I forget that? Transformation of coordinates. Okay, so R is square root of x squared plus y squared, little x squared plus little y squared. Theta is inverse tangent of y over x. Z is just z. Okay, and the inverse transformation says x is r cosine theta, y is r sine theta, and z is just z. Okay, Jacobian can be computed similar to what's earlier, but let's write down the helix first. Okay, the Jacobians helix. Okay, let me just give the 3×3 matrix dr over dx, dr over dy, dr over dz, okay, d theta over dx, d theta over dy, d theta over dz. You see, this will be very similar to the matrix for polar and Cartesian coordinate transformation, because z is unchanged, right? R theta, you just add an extra dimension, dz over dx, dz over dy, dz over dz. Okay, as you should get x over r, y over r, 0, and dx, hang on a second, what's that? What's that earlier? So this is minus y over r squared. There you go. Minus y over r squared, x over r squared, and 0, little r squared, okay? And finally, the last line is very easy, 0, 0, 1, boom. Okay, the inverse transformation, you get dx over dr, dx over dy, d theta, dx over dz, all right, dy over dr, dy over d theta, dy over dz. This is just nothing but multivariable calculus. dz over dx, dz over dr, dz over d theta, and dz over dz. Okay, that's the 3×3 matrix. Keep going. The upper 2×2 block is the same as we did earlier, so this is just cosine theta minus r sine theta. Okay, here you get sine theta, r cosine theta, 0, 0, 0, 0, 1. Right? That's it. That's it. Okay? And then, you know, right after that, we can state what 409 says. What does 401 says? What does that say? You have the Jacobian. You can now write down the transformation law. Right? Given, where do we have that? Yeah. 401, it should say this. It should say this. So you have x, y, z, and r theta z. How should things transform? What does 401? Sorry. What does 491 say? What does 491 says? You should have, you're transforming from x, y, z to r and r theta z, right? So big R is what? It should transform according to the forward Jacobian. It should transform according to the forward Jacobian. So R should be, okay, x dr dx. This is what it says. So a verbal description would be, a verbal description of 491 would be the original component times the forward Jacobian. Or actually, it's the, in terms of matrix multiplication, it should be the forward Jacobian times the original component. Right, so let's do that. This is the forward Jacobian, not the inverse Jacobian, okay? So use this one, x times dr dx plus y dr dy plus z dr dz. And what does that say? It should be big X, little x over r plus big Y, little y over r plus 0. Okay, so we write nothing. Okay, so that's the first transformation. Second, big theta. How does big theta behave? Well, use the second rule. X times d theta dx plus, yeah, so is everything clear now? Y times d theta dy. Yeah, I was confused because I thought big X, Y, and Z are the coordinate system. No, they're not. These are components of a contravariant vector. So I'm just rewriting 491. Okay. So this is very important. Okay, so if you guys get it, say something in chat. Okay, hopefully, because I was confused too. Minus big X, y over r squared plus big Y, x over r squared. And big Z is what? Big Z is big X dz over dx plus big Y dz over dy, and big Z times dz over d little z. So it's just big Z. And take a look. This is the same as we did earlier, huh? Is that the same? Yeah, it is the same because you see x over r is just cosine theta. Y over r is sine theta, so everything checks out. So that's the formula. Okay, so yeah, let's keep rewriting this. So this is big X times cosine of theta plus big Y times sine of theta. The transformation law of contravariant vectors between Cartesian and cylindrical coordinate. Awesome. We did it, right? So that's what it says. And of course, you can verify this. For as an example, you can do this for helix. Okay, so helix is what? So helix on the xy plane is just like a regular circle. Okay, helix x is cosine of t, y is sine of t, and z is just t. In the vertical direction, it like moves up linearly. Okay, in the xy plane, it does a uniform circular motion. Okay, and then what is the description in the polar coordinate? Little r is constant 1, theta grows like t, and z also goes like, actually, you know what, this should be little z. I'll read your comment in a second, all right? So little z is t. That's unchanged. Marco says, to keep in mind, the transformation law for contravariance is the product between the formal variable and the elements of the Jacobians. Yes, exactly. So you know what? It's perhaps helpful to write in the definition part, okay? It's perhaps useful to write it as a matrix multiplication. So basically, this is what it says. In matrix form, let's write it in matrix form. In matrix form, right? We already seen the matrix form in this particular example here. So this really just says A bar 1 all the way to A bar n column vector. Okay, is what? This is A bar n. This is hang on. Perhaps it would be nice to keep the, I don't know, like I have choice here. I can represent it as a row vector or I can use it as a column vector. What do you guys say? I have choice here, right? So tentatively, perhaps later on we will change our choice. So for now, let's just keep it as a column vector. But the idea is you would move the matrix to the left and then times the original vector a1 all the way to an. So this is also 491. They say that completely the same thing. One uses the summation convention, one uses the linear algebra conventions or the linear algebra definition for matrix multiplication. Okay, so the matrix starts from dx bar 1 over dx1, goes all the way to dx bar 1 over dxn, and it goes down to dx bar n over dx1. Sorry, downstairs. Downstairs should be, yeah. There's no new math here, right? Well, except for 4.1. That's a new math. I'm just saying that you can write this in a different way. I'm just rewriting 491 in a matrix form, if that helps. I mean, we do whatever we can to use our existing knowledge base to help us out. But eventually we want to get rid of this matrix form, because eventually you have too many indices, and linear algebra, the traditional linear algebra, isn't rich enough to incorporate those. Okay, so anyway, yeah, so that's the multiplication for 9. As I was saying, you can, of course, can you write this as a row vector? Can you rewrite this as a product between row vector and a Jacobian? Can you do that? I mean, we've checked it here. We checked it here. So let's do a little experiment here. So if we, let's say, oh, if you take the transpose, then it would transpose the Jacobian. No, that's not what we wanted. So it has to be this. It has to be like this. So imagine if you change this into a row vector notation. So let's say you have x bar dot 1, x bar dot 2. You take the transpose. You remember the law of the transpose. You have to transpose the matrix, right? So the order is reversed. So x dot 1, x dot 2 on the right hand side, and then you got to transpose the matrix, which messes up the structure of the Jacobian. So if you transpose that, you get dx bar 1 over dx1, and then dx bar 1 over dx2. And that's not usually how you write Jacobian. Jacobian has this format that the rows have identical dependent variables. Yeah, row vector and matrix multiplication on the right. So you see, but this is not a Jacobian anymore. This is the transpose of Jacobian. But in tensor analysis, we only deal with Jacobian and the inverse Jacobian. So this is not a Jacobian, this is Jacobian transpose. So I think this is unnatural. Even though it's equivalent, but I think it's unnatural. This is the correct matrix form. Okay, so yeah, thanks for raising that point, Marco. All right. So yeah, I was saying that you can do this as an exercise. Basically, what we did for the 2D example. So you have the helix, and the tangent vectors would be x dot equals minus sine, y dot equals cosine, and z dot equals 1, r dot equals 0, theta dot equals 1, and z dot equals 1. All right, and verify the law of transformation. So go ahead. So you call this the big X, the second the big Y, the third the big Z, okay, and 0 the big R, 1 the big theta, and Z dot the big Z. So you want to verify this. And when you verify that, be sure to use to use the coordinates, to use the to use the coordinates as the coordinate on the curve. Okay. Anyway, so I think we can move on now. Okay. So yeah, let's see. Now we're getting on to the topic of covariant vectors. The covariant vectors. All right. So the covariant vectors. Okay. So let's see. This is what the textbook says. Actually, the exposition is very short. The exposition is very short, but I think we will enrich this in some form. Okay, covariant vectors. Because this section seems to lack examples. Okay, so now we consider the scalar point functions. Actually, that's fine. That's fine. I think this section is perfectly adequate. It says now we consider the scalar point function, like what? Like a temperature field. Scalar point function. So it's a scalar valued function of a point in Vn. Okay, which we usually visualize as a level set. So imagine this. This is E2, okay, V2. This is level set, like isothermal curves. Okay, in case you guys don't know, just a couple of days earlier there was this horrible smog in Ontario, Canada, because we have wildfires, and I was tracking the air quality chart every day, and the whole screen is like red. Okay, PM 2.5 index when it comes to that is red, and certain areas are yellow, orange, but most part is completely red. Okay, so that would be the what's that the level curve for the PM 2.2 index, to PM 2.5 index. Okay, so this is a scalar value function. It is a function of a point. That's what we're getting to. That's the main idea here. Once again, it is a function of just pure space. It has nothing to do with coordinate system. Okay, so it's a scalar value function of points in Vn. Let's write it as phi. So phi, this is just a scalar. Okay, there's no index anymore. So this phi is a function of x1, x2, and xn. So imagine you have a coordinate system to describe points, x1 all the way to xn, and phi really is a function of a point. It shouldn't be coordinate dependent. Okay, so what's the gradient vector? What's the gradient vector? Well, actually, let's not call this the gradient vector, but let's just form the n-tuple. Let's just form the n-tuple. You can imagine for the moment that x1 all the way to xn are Cartesian, okay? If that helps. You can imagine these are Cartesian, and we're going to consider the n-tuple, which is the list of partial derivatives, okay? Consider d phi over dxi, okay? d phi over dxi, which is the collection d phi dx1, or the n, yeah, it's an n-tuple, it's not a collection. Okay? Collection means a set, this is the n-tuple. d phi over dx2 all the way to d phi over dxn. Once again, I was saying you may, for the moment, consider x1 all the way to xn as Cartesian coordinate. So this way, this is the formula for the gradient. Right, this is a gradient. And now let's do a coordinate transformation. let's do a coordinate transformation, say from xi to yi. Meaning yi is a function of x1 all the way to xn. Okay, so now can we form the new tuple, which is d phi over dyi? Can we do that? What's d phi over dyi? Well, d phi over dyi, using the chain rule, is just d phi over dx alpha times dx alpha over dyi. All right? It's just the chain rule. By the chain rule, you get that. And guess what? That's another coordinate transformation law. You get the relationship between d phi over dyi and d phi over dx alpha. And you see, they're related by the inverse Jacobian now. This is fundamentally different compared to the covariant vector, no? So this is important. So now we have a second class of vectors. A mathematician wants to call them covectors. So contravariant vectors are just vectors in modern mathematics. But in physics, still, people talk about covariant vectors and contravariant vectors all the time. So this is not like dead terminologies, okay? So still in physics and engineering, this is still used all the time. But just that in modern differential geometry, you say vectors to mean contravariant vectors, and you say covectors to mean covariant vectors. Okay, so guys, I strongly recommend everyone to check out Chris, another YouTube channel. He many years ago did the whole series on tensor calculus, which is awesome. Okay, so now you have this new law, and let's make a definition based on that. Definition. Right. Definition. Definition. This is a definition for covariant vectors. If the vector components transform according to this law, then we call it the components of a covariant vector. If a bar lower I actually, you see why this is lower? Because here you have lower index. So now the lower index and upper index actually takes on meaning here. So lower index are components of covariant vectors, whereas upper index are components of contravariant vectors. A bar I equals A alpha times dx alpha over d x bar I. If this is a law, right, so given, if this is true given a coordinate transformation, given the coordinate transformation as I was saying, xi to xi x bar I, x bar I are functions of x1 all the way to xn, then we say, then ai lower index, okay, are said to be the component of covariant vector, of a covariant vector. So is everyone on board now? So that's the law. So this is 494, second law. This is how a covariant vector component transform. Okay. And here the author asked the rhetorical question: what is the difference between a contravariant and covariant vector? It is the law of transformation. Compare 494 with 491. Okay, we might ask why it was that no such distinction was made in elementary vector analysis. Right? In multivariable calculus, you probably didn't have this distinction. We shall answer this question in a later paragraph, so we're looking forward to that. Okay, but as of now, can we write 494 in matrix form? Can we do that? Remember, here we're dealing with the inverse Jacobian. The key here is absolutely the fact that we're using inverse Jacobian. So how would we rewrite this in a matrix form? While we can, right? Because later on in more complicated object, you have the full tensor definition. If you have the full tensor definition, then it will be difficult to write down matrix form anymore. So let's do so while we still can. Okay, so, well, what's the inverse Jacobian? Let's write that down first. So the inverse Jacobian is x dx1 over dx bar 1 all the way to dx1 over dx bar n, and it goes down to dxn over dx bar n, dx bar 1, and all the way to dxn over dx bar n. Right? That's the inverse Jacobian. So what's being summed over? Well, the upper index alpha is being summed over because that's repeated. So what's the upper index? Upper index stands for rho. Now rho is being summed over. You have to place the vector as a row vector, the a vector as a row vector. So you got a1 all the way to an this way, to ensure that the row index is being summed over. So that's the difference between row vector and column vector. You see, in linear algebra, by default, we only use we only use the column vector, right? And it seems like an odd notational choice, but it's chosen that way for a reason. Because it has to do with how matrix multiplication is defined. Has to do with matrix multiplication is defined. So now the idea is the gradient, right? Just imagine once again, imagine if in the motivation part, x1 all the way to xn are Cartesian coordinate, you get a gradient. A gradient is what we call linear form. Is a linear form. The gradient is a linear function whose value is a vector. Sorry, whose value is a scalar. It takes a vector and returns a scalar. So what does a gradient do? Imagine what does a gradient do. So the gradient in multivariable calculus, we visualize that as a vector. But really, what it does, it provides the directional derivative. Right? So imagine if you have a direction u, then the directional derivative du of phi is what? Is the gradient grad of phi dot with u. So this is what the gradient does, right? You don't really care about the vector on its own, but rather this functional, this linear functional. It takes a direction as its input and returns a number. You tell me which direction you want to go, and I tell you the rate of change along that direction. That's what the gradient does. So it's a linear functional. It's a measurement. It takes a vector as an input and returns a rate of change. It returns a scalar. All right, so let me just finish writing up this formula. I will read the comment. So this is a bar 1 all the way to a bar n. So that's the matrix form of the covariant transformation. So now you can think of contravariant as column vectors and covariant vectors as row vectors. Of course, we're talking about components here, okay? Question, what determines what our Jacobian and its inverse will be treated as usual? Like going from Cartesian, actually, here, it has to do with the order, right? The order. You have one coordinate first, and then you call the new coordinate bar, right? That's usually how we denote things. You see, the unbarred coordinates are the old ones. This is the old coordinate system, and that's the new coordinate system. That's a new coordinate system. I call this the forward Jacobian. That's not the standard terminology. Typically, that's just called the Jacobian. That's just the Jacobian. So it has nothing to do with Cartesian or polar. These are specific examples, but it has to do with how you choose one coordinate and then choose a second. The order is what determines so-called Jacobian or inverse Jacobian. Okay, so this is what we call a forward Jacobian. I call it forward Jacobian. In literature, it's usually just called Jacobian. It's the new is d new over d old, if that makes sense. Okay, so this is a Jacobian. So the Jacobian is d new over d old, which feels natural, right? The inverse Jacobian is what? The inverse Jacobian is d old versus d new. Once again, that feels kind of natural. All right, so now we have the definition. Of course, go ahead and verify things. Okay. That's the end of the section in the book, but let's go ahead and verify. Example. Give ourselves the usual, give us a familiar pair of coordinate system and a simple scalar field to differentiate with and check whether everything is still stitched together. All right, so let's just copy everything from earlier. Okay, just copy everything from earlier. Okay, I don't want to do this verification again. So there you go, two coordinate system, same business. But now we're not playing with a curve anymore. We're playing with a scalar field. Okay, so same business. Okay, verification can be omitted. I just want the pair of coordinate system and the forward backward Jacobian. All right, so let's go here. So this is recycled stuff. Okay, so we still have the same Jacobian and backward Jacobian. Okay, and now let's consider the transformation law. So suppose let phi equals phi of x1, x2. This is phi of x1, x2. What does the transformation law say? What does 494 say? 494 says, okay, it says d phi over d x1. Actually, d phi over dx. Hold on a second. Yeah, d phi over. This is new. Why is new? So d phi over dx bar I. Right, equals d phi over dx alpha, and then partial derivative of dx alpha over dx xi. Right, or in matrix form. Well, we just wrote down the matrix form earlier. It's now a multiplication of row vectors. So it is d phi over dx bar 1, d phi over dx bar 2 equals d phi over dx1, d phi over dx2. And then multiply by the inverse Jacobian. So inverse Jacobian is right here. Okay, save me some writing. So this is what we should verify. All right, so there's that. Okay, so now let's take a look at an example. For example, is d old over d new? Yes. Yes, is d old over d new? It should be, right? I said inverse Jacobian. D alpha, dx alpha, that's old. Old over new. See? Old over new. Old is Cartesian, polar is new. Oh, yeah, you're right. Here, there should be a bar here. Yeah, I missed that. Thank you very much. Yes. Yes, you're correct. Thank you very much. So I think we're okay now. So let's, for example, let's verify. Say phi of x1, x2 is what? Phi of x1, x2, say this is x1 squared plus x2 squared. So thank you, yeah. So it's just the length squared. It's just x squared plus y squared. So let's take that. So after the coordinate transformation, then phi of x1 bar as a function of x1 bar and x2 bar would be what? Would just be x1 bar squared. Would be just one x1 bar squared. So now let's calculate everything. So here you have d phi over dx1 equals 2x1. d phi over dx2 is 2x2. Right? And d phi over dx1 bar is 2x1 bar. And d phi over dx2 bar is 0. It does not depend on the angle. It's rotationally symmetric. All right. So do we have this? Do we have this law here? So on the left, it should be 2x1 bar. It should be 2x bar 1, okay, and 0, the row vector. Okay, and on the right, you should have 2x1, 2x2. 2x2, okay? And what's this? Well, it's here. Let's verify if still everything works out. Okay, let's do the multiplication, and this way you get 2x1 cosine of x bar 2 plus 2x2 sine of x bar 2. All right, and then the second entry would be 2x1 x bar 1 sine of x bar 2. Where did you pull out this phi of x1 bar? Oh, where does this come from? Well, because of the coordinate transformation, right? You see, remember x bar 1 is the radius. Here, x bar 1 is the square root of x. Yeah, I think I messed up an index here. x1 should be upper index. Yeah, so basically that's where the transformation comes from. Here we see x1 squared plus x2 squared is the phi, is the value of phi. And by the coordinate transformation law, it's just the radius squared. It's like x squared plus y squared equals r squared. Okay, I'm using the index notation for us to check the definition easier. Marco, did you get this? Because I mean, it's perhaps more suggestive if you use x and y are theta, but I'm just trying to use index notation that confirms with the definition. Okay, so yeah, there's no mystery in that. So it's just from the coordinate transformation law. Okay, so now let's multiply this matrix and verify 2x1. Oh, actually should be a minus sign here. 2x1 x bar 1 sine of x bar 2 plus 2x2 x bar 1 cosine of x bar 2. All right, let's continue. So perhaps we can use the expression for cosine and sine. That's perhaps helpful. So remember, cosine of x bar 2, cosine of this angle, this is just x1 unbar over the length, over the distance, x bar 1. So cosine would just be x1 over x bar 1. Okay, and 2x2 times, okay, sine would be x2 over x bar 1. As you can already see, oh, actually, can we see that? Yeah, almost. Okay, so the second entry is minus 2x1 x bar 1. Okay, x bar 1 times the sine is x2. This is x2. And x bar 1 times the cosine is x1. So the second term is indeed 0. Okay, so you get 2 times x1 squared plus x2 squared, but that's just x bar 1 squared, distance squared, over x1 bar and 0. So this is indeed 2x1 bar 0. Checks out. This should hold, but and now is indeed verified. Okay, so we're done. Okay, so yeah, this scalar field, of course, has level curves that are just concentric circles centered at the origin. If you really wanted to use the vector representation, like in calculus, the gradient vector is in the radial direction. So it is clear that it should not have a tangential component. All right, so that's the visualization, geometric meaning of this calculation. It's just that the transformation law checks out. All right. So yeah, so now we introduce the definition of, the definition of covariant vectors. Let me just perhaps go through. Yeah, let's. I'm going to skip a section for now and go straight into tensors. Okay, so here, because I want to end the stream with the definition of tensor, I skipped one section on dot product, but we'll come to that later. Okay, so here we have the definition of tensor. We're now in a position to define tensors. Okay, look at this monstrosity. Hang on, I'll answer your question in a second. This is what we're getting at. This is the monstrosity. Okay, Marco asked Ming one question: why is there so much covariance in physics? I don't know. They're both pretty useful. I can't comment which one is more common, right? I guess covariance is particularly very common when we discuss the metric. So like we will do that in later section, and we'll also do that in information geometry. So basically, when you measure distances, you use metric tensor. There are fields in physics that based on, actually I'm not very literate, okay, when it comes to that. So basically, what I can say is, for example, in information geometry, as I mentioned, you care about distances. And distances are based on metric tensors. And metric tensors are covariance. No. I'm like, by all means, like, just you're a physicist. I'm not. Okay, I don't know much. Like, I learned this stuff, like I said, about 10 years ago, without much applications of it. So my skill atrophied. All right. So I'm pretty much a newbie as well, because I never really got much experience working with the applications of tensors. So things just becomes less and less familiar to me. But basically, I vaguely remember there's such notion of vectors and covectors and contravariance, covariance, and whatnot. Right? I derived things similar to this about 10 years ago. But like it, as far as because I have the general overview, like the philosophy of what this is about. Okay, the Christopher symbol and what's that? The covariant derivative, right? You probably heard of that as well. But now I need to revisit everything, as if learning this for the first time. And hopefully, after doing that, I get a more so it's a more appreciation of all this business. Anyway, so here we're finally going to define tensors. The contravariant and covariant vectors defined above are special cases of differential invariance called tensors. The components of tensor are of this form. You see, what a nightmare, huh? You got T, R, you have R upper indices. Yeah, that's the idea. I mean, this is this community-driven learning experience, right? It's this, I don't pretend to be an expert, not at all, right? Like, I mean, I've been corrected many times. That's great, right? So it's difficult for individuals to get feedback, right? So I mean, I'm very lucky to have this sort of feedback for my own learning. Anyway, so yeah, this is the definition of tensor. So you can see why mathematicians despise this. Can you guys see why mathematicians despise this, even though it's very useful in physics? Like if we haven't done all those things earlier and just drop this right away, this will probably be very difficult to understand, right? So let's think about what this means. Okay, so the components of the tensors of the form T, upper indices A1, A2 all the way to AR, and lower indices B1, B2 all the way to BS, with indices run through integers 1 to all the way to n. One thing to pay attention is that the number of upper and lower indices don't have to be the same. There are R upper indices and there are S lower indices. And they don't have to, of course, the numbers don't have to be the same, okay? So the components transform according to this rule. Okay, so imagine what is going on. So still, we have the same setup. You have the unbarred coordinates as the old coordinates, and the barred coordinates as the new coordinate. Okay, so on the left you got T bar A1, A2 all the way to AR, and downstairs B1, B2 all the way to BS. So that's the components of the same tensor in the new coordinate. This monstrosity, I know, right? But let's try to describe this verbally. On the left-hand side, we have the components of the tensor T in the new coordinate system. That's the left-hand side. On the right-hand side, let's first ignore this factor now. Okay, let's first ignore this factor, but just take a look at the rest. So first of all, you got the old component. This is old. T, A1, A2 all the way to AR, beta 1, alpha. Sorry, this should be alpha because there's a summation involved. T, this is alpha. Okay, A1, A2, AR, B1, B2, BS. These are free indices. Okay, on the right you got T alpha 1, T alpha 2, T alpha 1, alpha 2 all the way to alpha R upstairs, and beta 1, beta 2 all the way to beta S downstairs. That's the old components. Okay, and then multiply by what? Multiply by, looks like there are looks like there are total in a number R of forward Jacobian. So the dx bar alpha 1, dx bar a1. Yes, the first part seems to be the terms of contravariant, exactly. So these are the forward Jacobian, which corresponds to the upper indices, aka contravariant indices. And now you have S factors of inverse Jacobian. See, this is d old versus d new, d old over d new. Of course, there are S terms of them. There are S terms. So, what I'm confused about is, why do we have this extra factor? We didn't have that earlier in our vector exposition, no? We didn't have that. And what is this big N? It didn't seem to indicate what is big N. Okay, so let's continue. Okay, here it actually says something about the big N. Okay, let's continue on this text. I think it's perhaps we need to write this ourselves, okay, and put some comment on it. We call the exponent big N of the Jacobian dx over dx bar the weight of the tensor field, right? So big N, that's a new thing, right? It's a new thing. Previously, we've been using big N equals 0. I don't know why there's a big N, but anyway, that's just an extra thing, I guess. Here it says the exponent big N of the Jacobian. By the way, this is backward Jacobian or inverse Jacobian. D old versus D new. Okay, and this is the exponent. Big N is the weight of the tensor field. If big N equals 0, we say that the tensor field is absolute. Okay, otherwise the tensor field is relative of weight N. I don't know where this would be useful, but well, we've seen earlier N equals 0 first. Perhaps that's the most common version. A tensor density occurs. A tensor density, I don't know what that is, for N equals 1. Right? Remember, here, this so-called Jacobian is the Jacobian determinant, by the way. This is the determinant. Perhaps this is useful for integration. Perhaps this is useful for integration. Because remember, in the change of variable formula, you have a Jacobian factor there. Because right now we still don't know, right? This is a definition. Perhaps this will come up useful earlier. But based on what we've been dealing so far, N equals 0. And it seems like that's the only two options. N equals 0 and N equals 1. Okay, a tensor density occurs for big N equals 1. The vectors of section 123 and 124. So 123 is on what? 123 is contravariance. Okay, so the contravariant part. Okay, this is 123. This part is 123. Okay. Could repeat, please? Yeah. Okay, I'll repeat it. Okay, so I hope in 495 everything is clear except for this factor here. Right? We've been seeing big N equals 0 in our examples,
but we're not sure what big N equals 1 does. I'm not quite sure at this point, but my speculation is that it might have something to do with integration. Remember, from multivariable calculus, the change of variable formula includes a determinant factor, right? So if you remember from calculus, the dx dy, the area element in Cartesian is what? So the area element in Cartesian looks like this, right? Dx dy. And then you have the area element in polar. There's a conversion factor between the two. So this is, say, this is r, so you get r d theta and dr. So you get r dr d theta. So that's the Jacobian. It's a Jacobian determinant. Perhaps this is for accounting for integration. Actually, that's why I'm not quite sure. So perhaps this is for that purpose, okay? So if n equals 0, which that's what we've been seeing so far, we say the tensor field is absolute. And if n equals 1, which seems to be the only other option, a so-called tensor density occurs, which is undefined at this point. Okay, this might come up useful later. I suspect it has to do with integration, but I'm not sure. Okay, the tensor of 495 is said to be contravariant of order r. Okay, this makes sense because there are upper indices, and covariant of order s. If s equals 0, if x equals 0 is purely contravariant, if r equals 0 is purely covariant. Otherwise, it's a mixed tensor. All right. So I think we should probably end the stream at this point. Okay. So next time we will do more exercises and more with general tensors. So, all right. So that's it for today. Thank you very much for joining the stream, and I'll see you guys next time.